Deep inside a storm cloud, in the cold dark several kilometers above the ground, something very small is happening. Two kinds of ice exist up there, at the same moment, in the same churning air, tiny crystals, light enough to be carried upward on rising currents, and heavier pellets called grapple, dense enough to sink slowly back toward the cloud's lower reaches. They pass each other in the turbulence, the crystals rising, the grapple falling, and where they meet, they collide. Each collision is too small to hear. Each one transfers a charge so slight it would be impossible to measure with any instrument a person could hold in their hand. But the cloud is large, and the turbulence is constant, and the collisions are happening by the millions in every passing second, and the effect of all those tiny exchanges accumulates in a way that has no clear upper limit. For a while, the crystals carry their charge upward toward the cloud's top. The grapple carries its opposite charge downward toward the base. And somewhere in the middle, between these two slow rivers of electricity moving in opposite directions through the frozen air, the cloud is becoming something more than weather. This process has a name. Scientists call it the non-inductive charging effect, but the name arrived after the understanding, and the understanding arrived after decades of observation, and the observation required people willing to fly instruments into the interiors of thunderstorms in small aircraft. The name is less interesting than the thing itself. What the thing itself is, simply, is this: a storm cloud can build a charge separation of tens of millions of volts across its interior without producing any visible change in its appearance. From below, the cloud looks the same as any other tall gray mass of water and ice. The light does not shift, no sound emerges. The enormous electrical tension building between its upper and lower regions is happening in complete silence, entirely out of sight, and the only outward sign that anything has changed at all is that the air between the cloud's base and the ground below has begun, very slowly, to feel the edge of it. The ground beneath the storm cloud carries its own charge, and that charge shifts as the cloud moves overhead. The negative charge accumulating at the cloud's base repels negative charge in the ground below, pushing it away, leaving a region of positive charge concentrated in the earth directly underneath the storm. Buildings stand in that region. Trees stand in it. Hills and towers and open fields all sit within this rearranged electrical geography, holding charge they would not otherwise hold, feeling a pull they would not otherwise feel. None of this is visible. A person standing in a field under a darkening sky would notice the wind changing, perhaps, or the air cooling, or the particular smell that arrives before rain. They would not notice that the ground beneath their feet had become, in a quiet electrical sense, a different place than it was an hour ago. What happens next happens in stages, and the stages are worth following carefully, because the visible bolt that eventually arrives is only the last of them, and in some ways the least of them. The first stage is called the stepped leader, and it begins when the electrical tension in the cloud's lower region finally exceeds what the air below can hold. Air is a very good insulator under ordinary conditions. Its molecules resist carrying current, and the voltage required to force a channel through undisturbed air is enormous. But the air below a charged storm cloud is not, by this point, undisturbed. It has been stressed, it has been pulled, and when the voltage across a particular region of air finally reaches the point where the air's resistance begins to fail, a small section of that air ionizes, its molecules stripped of electrons, made briefly conductive, and the charge in the cloud moves into it, not all the way to the ground, not even close, just a step, perhaps 50 meters. A narrow, invisible channel of ionized air extends downward from the cloud base for 50 meters, and then it pauses. The pause lasts approximately 50 microseconds, which is 50 millionths of a second. Then the process repeats, and the channel extends another 50 meters. It pauses again. It extends again. Each segment does not proceed in a perfectly straight line. The stepped leader branches and forks and wanders, following paths of least resistance through the air. And the result is not a single straight channel descending toward the ground, but an invisible branching structure spreading downward through the dark air, below the cloud, looking if it could be seen at all, which it cannot, something like a very slow, very delicate crack spreading through glass. The speed of the stepped leader's progress is slow by lightning's eventual standards. It advances at roughly 200,000 meters per second, which sounds fast in any human frame of reference, but lightning's frame of reference is not a human one, and by the time the return stroke arrives, the stepped leader's pace will seem almost leisurely in comparison. The whole downward progression takes somewhere between 10 and 50 milliseconds, a time short enough to be imperceptible to a watching eye, but long enough to be meaningful in the physics of what is happening. The leader is not racing toward the ground, it is finding its way. It is, in a sense, searching. Nothing about the stepped leader is visible to an observer on the ground. The ionized channel it creates carries no light that the human eye can detect. A person standing in the open air below a storm, watching the sky, would see nothing of what is descending toward them through the dark. The storm would look exactly as it had looked before the leader began. The clouds would move, the wind would push, the rain, if it was falling, would fall, and 50 meters at a time, invisible and silent, a conducting channel would be working its way downward through the air above them, branching and pausing, and branching again, steadily reducing the distance between the cloud's stored charge and the ground's answering charge until that distance became small enough for the next stage to begin. That next stage is called the attachment process, and it begins when the lowest tip of the stepped leader closes to within roughly 100 meters of the ground. At that point, something changes in the local electric field. The field near the tips of elevated objects, the peak of a tall tree, the corner of a rooftop, the top of a metal rod, intensifies to the point where those objects begin to produce their own upward-reaching channels of ionized air. These are called upward streamers. They are also invisible, also silent, and they extend upward from their origins by perhaps a few meters to perhaps a few tens of meters, reaching toward the approaching leader the way two magnets of opposite polarity reach toward each other across a gap. Most of them will not connect. Most upward streamers extend a little way into the air and then fade without meeting anything. But one of them, the one whose tip comes close enough to the closest tip of the approaching stepped leader, will bridge the gap. The two channels will meet. The circuit will close. The moment of connection between an upward streamer and a descending stepped leader is called the attachment point, and it marks the end of the invisible phase of the lightning process. Everything before this moment has been silent and unseen. What follows it is neither. From the attachment point, a wave of ionization races back up the channel that the stepped leader built, traveling now not downward, but upward, not at 200,000 meters per second, but at something closer to 100 million meters per second. And this return wave is the thing that produces the light and sound that a person on the ground would recognize as lightning. The return stroke, the thing that for most observers is the whole of what lightning is, though it is only the last act of a much longer process that has been unfolding quietly in the air above them. The return stroke heats the air inside the channel it travels through to approximately 30,000 Kelvin. The surface of the sun, the visible layer of it, sits at roughly 6,000 Kelvin. The channel through which the return stroke passes is, for the duration of its transit, about 5 times hotter than that. What is particularly worth sitting with is the width of this channel, something 5 times hotter than the surface of the sun, carrying hundreds of thousands of amperes of current, passes through a column of air that is between 2 and 5 centimeters wide. A thumb's width, a finger's width, all of that temperature, all of that current, all of that light, compressed into a channel no wider than the space between the middle knuckles of a closed hand. The air inside that channel does not merely heat, it expands explosively outward in every direction, and the pressure wave from that expansion is the sound that arrives, delayed by distance, as thunder. But the return stroke itself, the luminous pulse that produced both the light and the sound, lasts only about 200 microseconds, which is 2/10,000ths of a second, shorter than the fastest camera shutter most people have ever used. Over before the eye can register its beginning. What the eye does register is the light, a flash, and often a flicker. The flicker is worth understanding because it seems from the ground like a single bolt struggling to hold itself together, wavering, almost strobing. But that is not what is happening. What is happening is more orderly than that, and more interesting. The channel that the first stepped leader created and that the first return stroke traveled does not instantly cease to exist when the first return stroke is complete. The air in that channel remains partially ionized, not fully, not enough to carry the same enormous current as before, but enough to be significantly more conductive than the undisturbed air around it. For tens to hundreds of milliseconds after the first return stroke, that channel persists as a corridor of reduced resistance hanging in the air between cloud and ground. And if the cloud has more charge to release, if the region of charge that drove the first stroke has been depleted but adjacent regions remain charged, then a second discharge can travel down that already prepared corridor far more easily than the first one, carved its path through fresh air. This second discharge is called a dart leader, and it differs from the stepped leader in a key way. The stepped leader had to build its channel from nothing, advancing in discrete steps through resistive air. The dart leader travels a path already made. It does not step, it flows. It moves down the existing ionized channel at speeds roughly 10 to 100 times faster than the stepped leader, somewhere between 1 and 10 million meters per second, and when it reaches the ground, it triggers another return stroke up the same channel. That second return stroke looks to an observer on the ground like the same bolt flashing again because it is traveling the same path, lighting the same channel, producing light from precisely the same geometry that the first return stroke did. And if the cloud produces a third discharge, and then a fourth, each one will travel the same corridor and produce the same pattern of light, reusing the channel like a road that has already been cleared. A complete lightning flash, from the moment the stepped leader begins to the moment the last channel fades, lasts somewhere between 2/10 and 1 second. Within that second, most flashes carry 2 to 4 return strokes, some carry more. The flicker that an observer perceives when watching a bolt from a distance is the interval between those strokes made visible, the brief dimming between one return stroke and the next, the channel glowing and fading and glowing again in rapid succession, each stroke separated from the next by perhaps 20 or 30 milliseconds, a rhythm too fast to count, but just slow enough to be perceived as something other than a single continuous flash. It is worth dwelling on the arithmetic of what this means. The luminous part of the return stroke lasts 200 microseconds. The interval between strokes is roughly 20 milliseconds. In terms of its ratio, the flash spends more time between its strokes than it spends producing them. The light that fills the sky, the light that is bright enough to cast shadows and illuminate an entire horizon, is actually present for only a small fraction of the time a flash appears to be happening. The rest is the eye's persistence of vision, holding the image a little longer than the light itself held on, the retina carrying what the atmosphere has already released. The cumulonimbus cloud responsible for all of this is still up there while the strokes are happening, still turning and churning, still producing the upward drift of ice crystals and the downward sink of grapple, still running the collision process that built the charge in the first place. A single storm cell can generate dozens of flashes in the space of an hour. Not all of them reach the ground. The vast majority of lightning discharges happen entirely within the cloud, between different charged regions inside the same cloud mass, never touching the earth at all. The bolts that reach the ground, the ones visible to a person standing in a field or watching from a window, these are a minority of the total. The cloud's interior is where most of the activity lives, the slow, invisible rearrangement of charge happening in frozen air, too high and too dark for anyone to see. The turbulence inside a cumulonimbus is not gentle. Updrafts inside a large storm cell can reach speeds of 50 meters per second or more, and the ice crystals traveling in those updrafts are small enough and light enough to be carried wherever the updraft takes them. The grapple pellets, denser, heavier, each one formed around a nucleus of dust or ice, resist the updraft more effectively and begin to fall when the updraft velocity drops below the speed required to support their weight. The zone where the two populations overlap, where rising crystals meet falling grapple in the same turbulent region of air, is where the charging happens most intensely. That zone moves as the storm develops. It rises and falls with the cloud's internal dynamics. The charge distribution it produces is not static, but constantly shifting, and the stepped leaders that eventually form are tracing a path through an electrical landscape that is itself changing, which is part of why they wander and branch rather than descending in a straight line. The charge that the cloud accumulates before a flash is typically measured in coulombs rather than in the more familiar unit of volts, but the voltage gets at the scale of it more intuitively. The potential difference that builds between a storm cloud's base and the ground below it before a discharge can be anywhere from tens of millions of volts to something approaching 1 billion volts in particularly large storm systems. By comparison, the voltage in a household electrical outlet is 120 volts in North America, or 240 in most of Europe. The difference between those numbers and the numbers inside a storm cloud is not just a matter of degree. It is a difference in kind, the way that a tide pool and an ocean are both bodies of salt water, but exist at scales that have almost nothing in common in terms of what happens inside them. The air's insulation is eventually what fails. Air can hold an electric field of approximately 3 million volts per meter before it breaks down and begins to conduct. The potential gradients inside a storm cloud do reach and exceed that threshold, but not uniformly and not all at once. There are regions within the cloud where the field is stronger, where the geometry of the charge distribution creates a concentration, and it is from those regions that discharge begins. The stepped leader's first segment forms in the region of strongest field, where the air's resistance has most completely failed. From there, the leader propagates outward into regions of slightly lower field, and the process of each step is essentially the leader extending itself into the air, just beyond where the previous step made conducting, finding the next region where the field is strong enough to ionize the air and extending itself there. A person watching a storm from inside a building, with a window running with rain and the low sound of thunder moving through the walls, sees none of this. What they see, if a bolt is close enough, is a flash that lasts for the duration of a blink, a sudden illumination that makes everything outside the window briefly visible in sharp detail. The wet surface of the road, the branches of the trees, the outline of the roofline across the street, and then darkness again, and a few seconds later, the sound. The sound arrives after the light, because sound travels through air at roughly 340 meters per second, and light travels at speeds that, for distances of a kilometer or two, might as well be instantaneous. The gap between the flash and the thunder is simply the travel time of the sound. At 3 kilometers, it is about 9 seconds. The bolt itself happened 9 seconds ago. The channel that produced it has already cooled and dissipated. The thunder is arriving from an event that is, in every physical sense, already over. What lingers after a flash is not the channel, but its heat. The return stroke heats the air to 30,000 Kelvin in a fraction of a millisecond, and that air does not cool instantly. The channel expands. The shock wave moves outward. The remaining heat dissipates into the surrounding air over the next fraction of a second, and the ionization fades as the temperature drops. And within perhaps half a second, the specific column of air that held 30,000 Kelvin is already approaching ambient temperature again. The bolt leaves almost nothing physical behind. No mark on the air, no scar in the sky. The electromagnetic energy it carried is gone, distributed into the surrounding atmosphere as heat and sound and radio waves, and the visible trace of it is gone almost before the eye that perceived it has finished registering what it saw. Almost nothing. There is one exception, and it lives in the ground rather than the air. When a return stroke reaches the earth, the enormous current passing through sand or soil can fuse the substrate along the exact path of the discharge into a glassy tube. These are called fulgurites, and they form in milliseconds, and they preserve the shape of the lightning channel in permanent solid form. But the air above them holds no record at all. The sky through which the stepped leader descended and the return stroke ascended is already indistinguishable from any other patch of undisturbed air by the time the sound of the thunder has finished echoing off the nearest hillside. The cloud, if it is still generating charge, will begin the process again. The ice crystals will continue to drift upward. The grapple will continue to sink. The collisions will continue millions per second, too small and too quiet to hear. Another charge separation will build. Another stepped leader will form in the cloud's lower reaches and begin its invisible, branching descent through the dark air, 50 meters at a time, pausing for 50 microseconds between each step, finding its way through an atmosphere that does not record that it has been here before and does not hold the memory of the path the last leader took. And yet, when the next leader is close enough to the ground for upward streamers to form, the streamers will form from the same elevated objects that produced them before, the same tall trees, the same metal structures, the same ridge lines, because those things are still there, still elevated, still concentrating the local electric field at their tips. The geometry of the ground does not change between flashes. The physics of field concentration is the same the second time as it was the first, and if the air where the last return stroke passed is still, even faintly, more conductive than the air around it, still holding a residual ion density that reduces its resistance by even a small amount, then the new leader will feel that corridor just slightly as a path of lower resistance, and it will be drawn toward it, not compelled exactly, but inclined. This is how lightning comes to return. Not by memory, not by anything that could be called intention, but by the persistence of the conditions that made the first stroke happen, the elevation, the conductivity, the geometry, the residual warmth of the air, where 30,000 Kelvin passed only moments before. The physics does not reset between flashes. It continues. The next flash, when it comes, will flicker again. It will appear as a single bolt to any watcher on the ground, appearing and disappearing in the fraction of a second their eye can track. It will seem from a distance to be a single stroke. It will seem sudden, complete, and over. But inside that flickering, 3 or 4 separate return strokes will be traveling the same corridor in rapid succession, each one triggered by a dart leader flowing down the channel, the first stepped leader built, each one arriving within milliseconds of the one before, each one reusing the path that was already there. The corridor opened by the first stroke stays open, briefly like a door that has not yet swung fully closed, and the charge that remains in the cloud after the first stroke finds that door and moves through it, and then finds it again and moves through it again, before the air finally cools and the ions recombine and the corridor closes for good. 3 pulses, 4, each one arriving in the dark along a path already known, each one the same brief blazing transit through a channel only a few centimeters wide, hotter than the sun's visible face, carrying its current to Earth in a time too short to perceive. And then the dark again, and the rain still falling, and the distant sound of thunder moving slowly outward through the night air toward wherever anyone is listening. The tip of the Empire State Building's antenna stands 443 meters above the street, which means it stands 443 meters closer to the base of a storm cloud than anything else in that part of Manhattan. On a night when a severe thunderstorm moves across the city, the air immediately surrounding that narrow point of metal is not the same air as the air 100 meters away. It is compressed, distorted, altered in a way that has no visible sign and no sound, a concentration of electric field that makes that specific cubic meter of atmosphere fundamentally different from all the others above the city's rooftops. The building itself, from the sidewalk, looks as it always does. The change is happening only at the very tip, in the invisible architecture of charge, where the geometry of the structure is doing something that the surrounding air is not. This is where the myth of lightning and randomness begins to come apart. The idea that lightning chooses its targets by something like chance, that a bolt is as likely to fall here as there, that being struck once confers no particular relationship with the sky, turns out to rest on a misunderstanding of what lightning is actually looking for, and what certain places are quietly, persistently offering it. The Empire State Building is struck approximately 20 to 25 times each year. In a particularly severe storm, it has been recorded being struck multiple times within the space of a few minutes. These are not coincidences accumulating. They are the same physical logic repeating itself over and over, because the physical logic has not changed. The question worth sitting with is not why lightning strikes the same place twice. The more interesting question is why it would ever choose anywhere else. A tall conductive structure does something to the electric field around it that shorter or less conductive objects do not. The field lines, the invisible geometry of electrical force that fills the space between a charged cloud and the ground below, tend to concentrate at points, sharp points, elevated points, conductive points. Where the field concentrates, the force is greatest, and where the force is greatest, the air is most likely to begin conducting. In practical terms, this means that the tip of an antenna on a very tall building is a place where the invisible architecture of a thunderstorm's electric field comes to a kind of focus. The air around that tip is under a kind of pressure that the air around a low, flat rooftop is not. And when that pressure reaches the point where the air's resistance fails, what rises from the tip of the antenna is not passive, it is active. The building reaches upward. This rising charge is called an upward streamer, a channel of ionized air that forms at the tip of an elevated object and extends upward toward a descending leader. The streamer is invisible. It produces no light that any observer on the street would register, but it is moving, extending itself into the air above the building, and it is looking, in the only sense that physics uses the word, for a path of least resistance toward the descending channel of charge above. When the two meet, the circuit closes, the bolt appears. The building did not wait to be struck. It reached upward to make the strike happen, at that location, at that moment, because its geometry made it the most efficient place in that part of the sky for the exchange to occur. For a building like the Empire State Building, this is not an occasional event. It is a feature of the building's relationship with the electrical environment above New York City. An antenna, the height, the conductivity of the steel frame, all of it adds up to a persistent preferred address in the local electric field, one that thunderstorms find again and again, not because the sky has a memory, but because the physics is the same each time. After a lightning strike, the ground near the impact point is not quite what it was before. The charge that traveled through the strike channel does not vanish instantly at the moment the flash ends. A residual charge distribution lingers in the earth and in the objects nearby, a subtle rearrangement of the local electric field that can persist for several seconds. This is not something visible to anyone standing nearby. There is no glow, no heat that can be felt, no sign that anything is different. But the electric field in the immediate area has been reshaped, marginally, in a way that makes the same zone slightly more inviting to the next discharge than an area where no strike has recently occurred. Several seconds is not a long time in any ordinary measure of things. It is long enough, under some conditions, for a second stroke to follow a first. It is part of the reason that locations which have been struck tend to attract subsequent strikes, not only across years and decades, but sometimes within the same storm, within the same minute. The residual charge is one piece of this. Another piece is more durable. The plasma channel that a lightning return stroke carves through the air is not an instantaneous thing that vanishes the moment the flash is over. The air in that narrow corridor, a channel perhaps 2 to 5 centimeters wide, running from cloud to ground, along the path the discharge followed, has been heated to a temperature that briefly exceeds the surface of the sun, and in being heated that way, it has been ionized. The atoms in the channel have been stripped of their electrons. What remains in the channel's wake is a corridor of plasma, a region of air that is no longer an insulator in the way that undisturbed air is an insulator. Its resistance has dropped to a fraction of what surrounds it. The channel is still partially conducting when the main stroke has passed. This partial conductivity persists for tens to hundreds of milliseconds. In the time scale of a lightning storm, that is not nothing. It means the channel that one stroke carved is still open, in an electrical sense, after the stroke is complete. And what follows, in a multi-stroke flash, is called a dart leader, a pulse of charge that travels down that pre-existing ionized corridor at speeds of roughly 1 to 10 million meters per second, many times faster than the original stepped leader that first carved the path. The dart leader does not need to feel its way through neutral air the way the stepped leader did. It does not pause in increments of 50 meters, advancing by discrete steps. The path is known. The corridor is already there, already conducting. The dart leader simply follows it. This is why a lightning flash that appears to flicker is doing something more than flickering. Each pulse of light is a separate stroke, a separate discharge traveling back down a channel that the first stroke established. The channel is being reused. And if the channel is being reused within a single flash across a span of milliseconds, the principle extends outward to minutes, to storms, to years. The same physical logic that sends a dart leader back down a channel, milliseconds after the first stroke, also sends the next thunderstorm's leaders back to the same elevated, conductive field concentrating location they found in the previous storm. The timescales are different. The mechanism is the same. There is a certain satisfaction in this, the way there is a satisfaction in understanding that a river takes the same path through a valley, not because the river chooses it, but because the valley's shape makes that path the line of least resistance, and the valley's shape does not change between one rain and the next. Lightning finds the Empire State Building's antenna for the same reason. The geometry is stable, the physics is repeating, the strikes accumulate because the conditions that produce them are not going anywhere. Researchers who study lightning strike patterns over time have assembled maps of strike density, records drawn from years of accumulated data showing where lightning falls most often across a given region. What these maps reveal is not a scatter of points distributed randomly across the landscape. They reveal a geography. Certain hilltops appear as bright spots. Certain stretches of ridgeline show up year after year. Isolated trees on flat ground, particularly tall ones with deep root systems that reach moist soil, return as recurring marks. Bodies of water appear in characteristic shapes. The maps look to someone who knows how to read them like a portrait of the land itself, with certain features glowing more brightly than others, not because those features have been unlucky, but because they have been doing, consistently and patiently, the same things that make a place electrically preferred. The factors that show up in these maps are not mysterious. Once laid out plainly, height matters most directly. An object that stands 50 meters taller than the ground around it has changed its relationship to the electric field above it in a way that is measurable and significant. Conductivity matters too, which is why soil type appears in the data. Sandy, dry soil conducts electricity poorly. Moist, clay-rich soil conducts it well, and objects rooted in or grounded to well-conducting soil are more effective at completing a lightning circuit than objects in resistive ground. Vegetation height contributes to this, which is why the tallest tree in a stand tends to attract more strikes than its neighbors. Topography channels and concentrates the electric field in ways that flat ground does not, which is why ridgelines and summit areas show up so persistently in the density maps, not because lightning targets summits as places of interest, but because summits are simply closer to the clouds, more exposed to the field above, more likely to produce the upward streamers that meet descending leaders. All of these factors are stable. They do not change from storm to storm. The hilltop that attracted 10 strikes in one decade is still a hilltop in the next. The tall, isolated tree is still tall, still isolated, still rooted in the same soil. The antenna is still 443 meters above the street. This is why the map drawn from one decade of data looks substantially like the map drawn from the next. The preferred locations are preferred because of what they are, not because of what happened to them before. There is a particularly clear illustration of this in the way lightning and tall trees develop a kind of long statistical relationship over time. A mature oak standing alone in a field, say 30 meters tall, with a deep root system reaching into moist subsoil, its canopy extending well above any surrounding vegetation, is not, in the average year, struck by lightning. In any given thunderstorm passing overhead, it is more likely not to be struck than to be struck. But over 20 years, or 30, or 50, the accumulated probability changes character. The same tree, in the same field with the same roots, is going to attract upward streamers in a higher proportion of the storms that pass over it than any shorter plant nearby. The strikes, when they come, will come to this tree more often than to the grass at its feet. By the time the tree is 100 years old, if it has survived, the lightning scars on its bark are a record of its persistent position in the local electric field, not evidence of poor fortune, but evidence of stable geometry. What complicates the myth is that the myth is easy. The phrase carries a specific feeling, the sense of fairness restored, that having faced a difficult thing once, the difficult thing will not come again. People want this to be true of lightning for the same reason they want it to be true of other things. It offers a kind of comfort in the face of apparent randomness. If the first strike has discharged the danger, the space is now safe. The debt has been paid. But lightning does not operate on a logic of debts paid or fairness distributed. It operates on a logic of fields and conductors and paths of least resistance. And in that logic, a place that was struck yesterday may well be the most likely place to be struck tomorrow, precisely because the conditions that made it attractive yesterday are identical to the conditions that make it attractive today. This can be restated more plainly. A location is struck because of what it is, physically and geometrically. Being struck does not change what it is. Therefore, it continues to attract strikes for the same reasons as before, with the same probability, or in some cases, if its conductivity has been altered by char, or if the soil moisture near its base has been changed, with a slightly modified probability. The change, where it exists, is never a permanent immunity. It is at most a slight shift in the conditions that drive the same physics. The Empire State Building's 20 to 25 annual strikes are not the result of accumulated misfortune. They are a measurement of the building's persistent electrical relationship with the storms that pass over Manhattan. Each winter, the building stands at the same height. Each summer, the thunderstorm season returns. Each time the storms arrive, the antenna tip concentrates the field, the streamers form, the circuit closes, the count goes up by 1 or 2 or 5, and by the end of another year, the total is roughly where it was the year before. This does not make the building exceptional in any dramatic sense. It makes it consistent. The consistency is, in its own way, the more interesting thing. It means that lightning strike data, accumulated over enough time, becomes a kind of geological record, a slow portrait of a location's relationship with the electrical atmosphere above it, as stable and readable as a topographic map. The same bright spots appear, the same ridgelines glow, the same tall trees mark themselves in the data. The physics does not vary. The map reflects it. In the years since systematic lightning detection networks have been in place across parts of North America and Europe, the density maps they have produced have confirmed what physics would predict, that lightning fall is not distributed uniformly across the landscape, and that the departures from uniformity are not random, but structural. They follow the land. They follow the conductivity of soils. They follow the height and isolation of objects. In regions where this data is dense enough, researchers can identify individual trees, buildings, or topographic features that appear as persistent attractors across multiple years of records, not because the sky is revisiting them by choice, but because the physical conditions at those locations have not changed. And physical conditions are what lightning responds to. There is something quietly instructive in this, the way there is something instructive in any pattern revealed by patient accumulation of data. The pattern does not emerge in a single storm. It does not reveal itself in a single year. It takes the slow stacking of records, storm by storm, strike by strike, before the underlying geography becomes readable. The bright spots are bright, not because they were dramatic, but because they were consistent. Consistency, in the end, is what makes a pattern legible. The dart leader racing down a pre-existing ionized channel, milliseconds after the first stroke, moving at millions of meters per second, because the corridor is already open, already conducting, the resistance already reduced to a fraction of the surrounding air, is the same principle at the smallest time scale. The channel was opened once, conditions made it easy to use again, so it was used again, almost immediately, before the channel had time to close. What happens across milliseconds in a multi-stroke flash happens in slower and less direct form across years of storms, finding the same hilltop, the same antenna, the same isolated oak. The channel is not the same channel. The physics is. Somewhere in the middle of a field, in a part of the country where the soil is deep and moist, and a single oak stands at the edge of a tree line, the tree has been struck before. The bark on its southern face carries a long, shallow scar where the current found its way to the ground one August afternoon, years ago. The scar is fully healed over now, or partially so. The tree is still standing. It is still the tallest object in the field by a significant margin. Its roots still reach deep into conducting soil. When the next summer's thunderstorm passes overhead, and the cloud base lowers, and the electric field between the cloud and the ground begins to concentrate at elevated objects, the tree will again be among the most likely places for an upward streamer to form. The field does not know about the scar. The storm does not know this tree has been struck before. The tree's height and conductivity are what they were the day the first bolt found it, and the day before that, and the decade before that. The scar is the record. The tree is still the geometry. And the geometry is what will matter the next time a storm crosses that field. The residual charge in the earth, near a strike point, the ionized channel hanging partially conducting in the air for tens to hundreds of milliseconds after a return stroke, the field concentration at the tip of a tall conductive object, the stable topography of hilltops and ridgelines, and isolated trees, these are not separate phenomena that happen to accumulate around the same locations. They are expressions of the same underlying reality, that lightning moves through the path of least resistance, that the features of the landscape, which determine where least resistance lies, are largely stable, and that stable conditions produce consistent patterns. The myth of randomness dissolves the moment the physics is made plain. What takes its place is not a more frightening picture, it is a more ordered one. The sky above a thunderstorm is not throwing bolts at random and occasionally revisiting the same address by chance. It is following electric fields. The fields follow the land. The land does not change quickly. And so the pattern of strikes, read at sufficient scale and over sufficient time, is a kind of map of the land itself. A portrait drawn in charge and current of the hills, the trees, the buildings, and the soils beneath them. On a stormy evening in Manhattan, this is all happening at the tip of the antenna, invisibly, the upward streamers forming, the field concentrating, the dart leaders following the corridors already opened by strokes that preceded them by milliseconds. The circuit closing again and again, adding to a tally that has been climbing since the building first rose above the surrounding rooftops decades ago. The building does not accumulate anything from these strikes in any ordinary sense. The charge disperses into the ground, the channel cools, the air returns to neutral, and the count goes up by one more. Across the country, in the accumulated records of lightning detection networks, a certain hilltop in the Appalachians appears in the data for the seventh year in a row. The same coordinates glowing in the density map, consistent across years as the seasons cycle. A stretch of ridgeline in the southwest appears as a pale band of higher than average strike frequency, the same band present in every annual summary, the ridge itself unchanged, the pattern unchanging with it. A tall, isolated tree, somewhere on a plateau, in a region of very flat land, marks itself in the data again, patient and persistent, the tallest object for several hundred meters in any direction, doing what the tallest object tends to do. The map, read across enough years, is not a map of accidents. It is a map of conditions. It is a portrait of what the land offers to the physics of lightning, drawn slowly by accumulation, legible only to patience. The bright spots are consistent. The preferred locations persist. What looks like chance when read through a single storm or a single season begins, across years of careful record, to look like something else entirely, a stable and quiet geography of places the sky tends to find, not by choice, but by the reliable logic of what is there. A distant thundercloud sits over a flat stretch of open country, and it is glowing, not flickering with bolts, not lit from outside by anything visible, glowing from within, the whole body of it brightening and dimming in slow pulses, like something alive and breathing behind gray curtains. No bolt crosses the sky, no sound arrives. The light simply moves through the cloud from inside, turning it briefly pale, then releasing it back to gray. This is the kind of lightning most people have seen without knowing they were seeing lightning at all. It has a common name, sheet lightning, though that name describes the appearance rather than the cause. What is actually happening inside that glowing cloud is electrical in every detail, and it never touches the ground. Most lightning never does. Of all the lightning occurring on Earth at any given moment, somewhere between 3/4 and 4/5 of it happens entirely within a single cloud, beginning and ending in the air, leaving no mark on the surface below. This is intracloud lightning, and it accounts for the great majority of all lightning events worldwide. The cloud lights up because the discharge illuminates the interior from within, the flash contained inside the cloud's body, rather than escaping through its base. Seen from several kilometers away, with the individual bolt hidden by the cloud mass itself, this looks like a soft general brightening, a momentary translucence, the kind of light that seems to have no clear source. The thunder it produces is muffled and low, or swallowed entirely by distance before it arrives. The specific internal geography of a cumulonimbus cloud makes this almost inevitable. Charge separates at different heights within the cloud, strongly negative regions sitting at mid-levels, strongly positive regions concentrated near the top, with a smaller positive region, sometimes near the base. When the electrical potential between two of these regions finally exceeds the insulating capacity of the air between them, the discharge travels along the path of least resistance through the cloud's own body. The channel it uses is not so different in its essential physics from any other lightning channel. It is simply entirely airborne. The result is a flash that stays hidden, illuminating several cubic kilometers of cloud, and then going out, leaving no trace that anything happened except the slow rebuilding of charge that will eventually produce the next one. From the hillside where the cloud sits on the horizon, the light pulses again and again. Each pulse is a separate event inside the cloud. The interval between them, not a pause in the storm, but simply the time needed for enough charge to accumulate once more. It is possible to watch this for a long time without growing tired of it. The rhythm is irregular enough to be interesting, and the scale, a structure of ice and water vapor several kilometers across, lit from within by electrical discharges, has a quality that repays calm attention. The sound, if it comes at all, arrives long after the light and arrives as a low continuous rumble rather than a sharp crack, the sound having spread and softened over the distance it had to travel. There is another kind of lightning that almost never announces itself in this way, that tends to arrive without warning from a part of the sky that might appear relatively calm, striking far from the apparent center of a storm. It originates not from the negative charge regions that generate most cloud-to-ground lightning, but from the upper positive charge region near the storm's top. This is positive lightning, and it accounts for only 5 to 10% of all cloud-to-ground strikes. What makes it worth sitting with quietly is the scale of what it carries. A typical negative lightning bolt carries a peak current of around 30,000 amperes. Positive lightning can carry peak currents of up to 300,000 amperes, roughly 10 times greater. It tends to be a single stroke with no repeat pulses, which is why it does not flicker. One immense pulse, and then stillness, because the discharge originates high in the cloud and must travel a much longer path to reach the ground. Positive lightning can strike at considerable distances from the storm's center, sometimes several kilometers ahead of the visible rain, occasionally under a sky that is partly clear overhead. The bolt has traveled horizontally through the upper atmosphere for some distance before descending, which is why it can arrive where the immediate surroundings give no particular warning. The flash itself tends to be longer in duration and broader in appearance than the narrow channels of negative lightning, and the thunder it produces is often a single deep concussive sound, rather than the sharper crack more commonly associated with close strikes. In open landscapes, a positive lightning strike leaves a scorch mark in dry grass or soil that speaks to the energy it carried, but the strike is over before the sound reaches anyone standing at any significant distance. The phenomenon produces its own particular stillness, one stroke, no flicker, the energy of it absorbed by whatever the discharge chose, and then the sky going quiet again, holding its own counsel. The electric field near the ground rebalances slowly after the passage of a charge that large. Positive lightning is well understood in its mechanics, even if its relative rarity means most people will never knowingly observe one. There are other atmospheric electrical phenomena that sit at the edge of understanding in a different way, observed for centuries, documented carefully, and still not fully explained to anyone's complete satisfaction. Ball lightning occupies this position. It has been reported across cultures and centuries, described in terms consistent enough to suggest that people have been observing something real, and yet the mechanism behind it remains genuinely open. The accounts share certain qualities. A luminous sphere, roughly the size of a grapefruit or sometimes larger, appearing during or after a thunderstorm. Light that is steady rather than flickering, usually described as white, pale yellow, or pale blue. Movement that seems largely independent of air currents, drifting through rooms, passing through or near windows, traveling parallel to the ground at roughly knee height or somewhat above it. Duration of several seconds to a minute or more. A disappearance that is either silent or accompanied by a faint pop, leaving no mark or leaving a faint smell behind. These details appear in reports from different countries, different centuries, different people with no knowledge of each other's accounts. Whatever is being seen, it is consistent. For most of scientific history, ball lightning occupied an uncomfortable category, too widely reported to dismiss, too poorly understood to explain. Plasma physics offered some candidate mechanisms. Microwave radiation theories were proposed and partially modeled. Oxidizing silicon nanoparticles were suggested. None of these accounts satisfied all the observed properties cleanly, and the phenomenon's rarity and unpredictability made controlled study nearly impossible to arrange. Then, in 2014, a research team in China working in the Qinghai region was conducting spectroscopic measurements of ordinary lightning from a distance of roughly 900 meters when a ball lightning event occurred naturally in their field of view. They had their instruments running. The sphere appeared near the ground following a cloud-to-ground strike, drifted for approximately 164 seconds over a distance of about 10 meters, and then faded. The spectrograph recorded the emission spectrum of the ball throughout its visible duration. When the team analyzed the data, they found emission lines consistent with silicon, calcium, iron, and other elements, the kinds of elements found in soil. The paper, published in Physical Review Letters, proposed that the ball lightning had formed from vaporized soil material at the site of the lightning channel, some process within the plasma producing a self-sustaining luminous structure for the duration of the observation. The study was careful about what it claimed. The spectroscopic data described what this particular ball lightning event was made of, or at least what it was emitting, more clearly than any previous documented observation. It did not claim to resolve all the questions around all ball lightning events, or to provide a complete account of the sustaining mechanism. The phenomenon remained, after the study, better documented than before, and still not fully explained. The honest position is that this was one high-quality observation of a rare and poorly understood thing, and that one observation moved the picture meaningfully without completing it. The sphere drifting over the ground in Qinghai, pale light, soil elements glowing in its spectrum, lasting less than 2 seconds, was real in the sense that the instruments recorded something, what sustained it, what the governing physics of its internal structure was, why it held together for the time it did before fading. These questions remained open when the paper was published, and remain open now. That is the shape of knowledge around ball lightning, not a mystery in the dramatic sense, but a gap that careful instruments have partially filled, with more to fill still. Far above any cloud where intra-cloud lightning pulses silently, or where positive lightning gathers its enormous charge, there is another layer of the atmosphere where electrical events occur that were entirely unknown to science until a video camera happened to record them by accident. This layer is the mesosphere, beginning at roughly 50 kilometers above the ground and extending to around 85 or 90 kilometers, well above the weather, in the region where meteors leave their trails, where the sky has shaded fully into black. For most of human history, nothing electrical was known to happen here in connection with thunderstorms. There was no particular reason to expect anything. In 1989, researchers at the University of Minnesota were testing a low-light video camera by pointing it at the night sky above a distant storm. They were not looking for anything specific in the upper atmosphere. The camera was recording, the researchers were doing other things, and somewhere in the footage afterward, they found something they had not expected. Brief reddish flashes above the thunderstorm, at altitudes far higher than any cloud, visible for only a few milliseconds before fading. The storm was below, the flashes were above it. The geometry was wrong for anything in the standard account of what a thunderstorm does. The phenomenon was eventually named a sprite. The name is informal. The scientific literature sometimes uses the term red sprite to distinguish the most common form, and it was chosen partly because the phenomenon seemed to belong to the same loose family as elves and jets, other upper atmospheric electrical discharges discovered around the same period, all of them named with a kind of lightness appropriate to things that had been invisible to science for so long. The naming reflects something real about how these phenomena feel when described. They belong to a region of the atmosphere that is generally thought of as empty, as mere distance between the ground and space. And finding active electrical processes there has a quality of discovering that a room long thought to be unoccupied has been quietly busy all along. A sprite occurs above a powerful positive cloud to ground lightning strike. The enormous current of a positive stroke deposits charge rapidly at the top of the ionosphere, disturbing the electric field across the mesosphere in a way that can trigger a discharge in air so thin that ordinary lightning could not form there. What appears on camera, when one is pointed at the right altitude at the right moment, is a reddish column or cluster of columns above the storm, sometimes with a brighter cap at the top and a diffuse red glow spreading below it, the whole structure resembling a jellyfish, loosely, a central column with tendrils or filaments extending downward. The entire event lasts a few milliseconds. It is red because the discharge excites nitrogen molecules at those altitudes, and nitrogen at low pressure emits in the red part of the spectrum. The color is genuinely there. It is not an artifact of the camera. At the scale of the storm viewed from the ground, sprites are invisible. They are too brief, too dim against the night sky, and positioned above rather than within the visible storm structure. An observer watching lightning from a hillside has almost no chance of registering one without equipment. The research that established sprites as a real and regular phenomenon required dedicated low-light cameras operated from high ground or aircraft pointed at the altitude range where sprites occur. Watching storms at distances of 100 kilometers or more, where the geometry allowed the upper atmosphere to be visible above the storm rather than lost behind it. Since the initial 1989 recording, many thousands of sprites have been documented. The phenomenon is now understood to occur regularly, associated with the class of powerful positive strikes that are themselves relatively uncommon. So sprites are not continuous, but they are frequent enough to be part of Earth's regular electrical repertoire. Pilot reports of unusual lights above storms stretch back many decades, and some researchers believe that historical accounts of upper atmospheric lights seen from ships and mountainsides may include sprite observations. The phenomenon is recent only in the sense of its formal documentation. It is old in the sense of having always been there, above every sufficiently powerful positive strike, in a layer of atmosphere that almost no one was looking at from the right angle. The reddish jellyfish shape hangs for its few milliseconds above a storm that has no idea it produced it, and then it is gone. There is something quietly satisfying about the geometry of a sprite, the storm below generating the conditions, the mesosphere above receiving and responding to them, the two systems connected by an electrical influence traveling upward rather than the familiar downward. It reverses the intuitive direction. Lightning goes down, and then something goes up in response, not as heat or light rising from the strike point, but as a separate discharge in a separate layer, triggered by the pulse from below. A slightly different geometry governs another phenomenon in this same altitude range, discovered in roughly the same period. Where sprites are vertical structures above a storm, elves expand horizontally. The name stands for emission of light, and very low frequency perturbations due to electromagnetic pulse sources, which is the kind of scientific backronym assembled when researchers want a memorable label for something they need to distinguish clearly from nearby phenomena. Setting the acronym aside, the event itself has a different quality from anything else in this range of the atmosphere. When a powerful lightning return stroke occurs, the current flowing in the channel produces an electromagnetic pulse, a rapid change in the electromagnetic field that propagates outward at the speed of light. This pulse reaches the base of the ionosphere at around 90 kilometers altitude in roughly 300 microseconds. When it arrives, it briefly ionizes the lower ionosphere in the region it reaches, causing that region to emit light. Because the electromagnetic pulse expands outward from the lightning channel as a growing sphere, the intersection of that sphere with the flat base of the ionosphere is a ring, a circle of light, centered on a point above the storm, expanding outward as the pulse front continues to travel. The ring reaches its maximum size in under a millisecond, expanding to a diameter of up to 300 kilometers before fading. The whole event is over in less time than it takes for a single frame of ordinary video to pass. An Elvis scene from directly below would be invisible. It is above the observer. Seen from an aircraft at altitude, or documented by high-speed cameras operated from the right position, it appears as a disk or ring of faint light appearing above the storm and immediately growing outward, its outer edge moving away at a speed determined by the expanding wavefront of the electromagnetic pulse. The light is faint enough that it requires dedicated instruments to record reliably. The duration is so brief that standard video cameras capture it only as a barely perceptible brightening in a single frame, if they capture it at all. High-speed cameras operating at thousands of frames per second can resolve the expanding ring shape, which is how the phenomenon's geometry was established. 300 kilometers across in under a millisecond, the scale is useful to sit with. The distance from one edge of the Elve to the other, at maximum extent, is greater than the distance across France. The time required to reach that extent is a fraction of the time required for a single lightning bolt to complete its return stroke. At 90 kilometers altitude, in the layer of atmosphere that connects the weather below to the charged ionosphere above, something that large forms and fades in a period too brief for any human nervous system to consciously register. It is easy to spend a long time with this category of phenomena, the things happening in the upper atmosphere in connection with thunderstorms, and to arrive at a particular kind of calm, not because the scales are comforting in themselves, but because the discovery of each successive layer above a storm suggests that the sky has more depth than any single view of it implies. Looking up at a thundercloud from below, the storm seems to be a bounded thing: cloud, lightning, rain, wind. The view from above, or from the instruments, adds a mesosphere full of sprites and jets, an ionosphere responding to electromagnetic pulses with expanding rings of light. The whole structure connected by electrical processes that had no place in any standard account of a storm until careful instruments found them there. The sprites do not change the storm below. The elves do not alter the cloud that produced them. These are responses, traces, evidence of influence traveling upward and outward. The storm produces them as a side effect of doing what it does, and the upper atmosphere receives them and briefly lights up and returns to its ordinary state, and neither system is aware of the exchange in any meaningful sense. The exchange happens regardless, in the dark above every sufficiently powerful positive strike on every night when the right conditions align anywhere on the planet. A cloud over a flat landscape is still glowing from within, the same soft pulsing it has maintained for the past hour. The sheet lightning inside it, illuminates ice crystals and water droplets that will never become a bolt reaching the ground. Far from the storm, a piece of open ground holds the faint scorch of a positive strike that arrived under a partly clear sky, one enormous pulse with no repeat, the grass still bent flat in the immediate radius of the discharge point. In the research literature, somewhere in a data archive in China, a spectroscopic record shows the emission lines of soil elements glowing in the spectrum of a pale sphere that drifted for 164 seconds above the ground, 900 meters from the instruments, and then quietly stopped. Above a storm in some part of the world tonight, a reddish column hangs for a few milliseconds in the mesosphere at 60 kilometers altitude, its nitrogen-excited light too brief and too faint for any ground observer to register. And then it dissolves. Higher still, at 90 kilometers above Earth, above the weather, above the clouds, above the layer where sprites occur, at the base of the ionosphere, where the last traces of ordinary atmosphere blend into the near vacuum of near space, an expanding ring of light reaches outward in every direction from a point above a thunderstorm. It covers ground measured in hundreds of kilometers in the time it takes for a candle flame to move 1 millimeter in a breeze. The air at that altitude is too thin to carry sound. No thunder will ever reach there. The electromagnetic pulse arrives without announcement, ionizes the lower ionosphere in a spreading circle, produces a ring of faint light that no human eye below will see, and fades. This is happening somewhere above the planet right now. It has been happening for as long as there have been powerful lightning storms and an ionosphere above them, which is a very long time. The instruments that record it are recent. The phenomenon itself is old and unhurried and entirely indifferent to whether anyone is watching, continuing in the dark above every qualifying storm, the ring of light expanding to its full width and then releasing, the ionosphere returning to its ordinary steady state, the storm below already building the next discharge, the whole system cycling without urgency, carrying on. The cloud on the distant horizon glows once more, softly from within. The sound has not yet arrived, and may not arrive at all. The light holds for half a second, fades, and the cloud returns to its gray bulk against the darker sky. Somewhere far above it, in a layer of atmosphere too high for weather and too low for stars, the sky is doing things that require patience and the right instruments to find. A reddish column here, an expanding ring there, each one brief and immense and entirely silent, happening in the dark above all the ordinary rain. A field outside Philadelphia on a June evening in 1752 smelled of rain and warm earth. The sky above was low and gray, moving with the weight of a storm that hadn't quite broken yet. A man stood in that field holding a length of string, the other end of which disappeared into the cloud cover above, and he was waiting for something to happen to his knuckle. Benjamin Franklin had been thinking about lightning for years before he stood in that field. He had read the accounts from Europe. He had corresponded with scientists in London. He had already proposed in print the idea that storm clouds were electrically charged bodies, not divine instruments, not mysterious forces, but physical objects accumulating charge in the same way a glass rod accumulates charge when rubbed against wool. What he needed was a demonstration. The kite was a practical solution, a silk kite with a metal wire running to its spine, a length of hemp twine as the line, and a metal key tied at the bottom where the line met his hand. The key was the crucial element. If the cloud above was electrically charged, some of that charge might travel down the wet twine and accumulate on the key, and a knuckle brought close enough would draw a spark. The hemp fibers on the twine began to stand on end. That was the first sign. The individual fibers rose away from the cord and straightened, reaching outward into the charged air, and Franklin would have recognized this immediately for what it was. The same effect he had observed in the laboratory, the mechanical evidence of charge building along a conductor. He brought his knuckle toward the key. A small spark leapt between them. It was not a dramatic event by any outward measure. A quiet field, a gray sky, a man standing alone with a kite string. The spark itself was small, the kind of thing a person might produce walking across a wool rug in winter. But what that spark confirmed was not small at all. Storm clouds were electrically charged. Lightning was a very large electrical discharge. The same phenomenon that Franklin had been demonstrating with glass rods and Leyden jars in his parlor was happening above him on a scale that dwarfed any laboratory apparatus, and he had just closed a circuit between the two. The idea had been correct. What made the kite experiment remarkable in the long account of how people have come to understand the natural world was not only what it proved, but how quietly it proved it. There was no instrument array, no team of assistants, no elaborate apparatus prepared over months. There was a kite, a key, and a man willing to stand in a field during a storm and pay careful attention to what his knuckle told him. The rain would have arrived soon after. The field would have gone dark. Franklin would have walked back toward the lights of the city with the knowledge that something very old and very large had just been connected, for the first time, to something small enough to hold in a hand. The spark he drew from that key was in its own way the same thing happening above him in the clouds. The difference was only one of scale, and the understanding of scale was for Franklin the whole point. In the centuries before that evening in Philadelphia, lightning had remained in a category apart from the physical world that human beings measured and reasoned about. It was acknowledged as powerful, as visible, as clearly capable of setting things on fire and splitting trees, but it was not understood as a mechanism. It did not have parts that could be named or a process that could be followed. After the kite and the key, it had both. The change this made to how people thought about the sky was not immediate. Changes of that kind seldom are, but it was real and it was permanent, and it began in a quiet field in the rain. Franklin himself moved on to practical applications quickly. Within a year, he was describing pointed metal rods grounded through a conducting wire to the earth that could draw charge gradually from the air around a building and prevent the sudden discharge of a full lightning strike. He had not only identified what lightning was, but had proposed the first systematic method for managing it. Whether the metal rod drew charge quietly from the cloud or simply provided a preferred conducting path for a strike that was going to occur regardless, remained a point of some discussion among natural philosophers for years. The outcome was the same either way. Buildings fitted with grounding rods fared better in lightning storms than buildings without them. The experiment in the field had, within a few years, changed the shape of rooftops. Not all encounters with lightning in those same decades had outcomes as constructive as Franklin's. In the city of Brescia in northern Italy, in August of 1769, a bolt struck the tower of the church of San Nazaro at a moment when the consequences extended far beyond the building itself. The Republic of Venice had for years been using the vaults beneath the church as a storage facility for gunpowder, a common enough practice in an era when secure stone buildings served many purposes simultaneously, and when the idea of positioning large quantities of explosive material beneath the structure open to the sky was not yet understood as the arrangement of hazards that it clearly was. The church's tower was the highest point in that part of the city. On a stormy August night, it was also the most likely point of attachment for a descending electrical discharge. The bolt came. The church received it. The charge traveled through the stone and into the vaults below, and in the vaults below were approximately 90,000 kilograms of gunpowder stored by the Republic of Venice. What followed happened in less time than any account could capture in words. The vault detonated. The church ceased to exist. 1/6 of the city of Brescia was destroyed in the moments that followed, and by the time the dust had settled and the accounting was made, approximately 3,000 people had died. A single bolt of lightning, one discharge, and one thunderstorm on one evening in August had, through the specific accident of where the gunpowder happened to be stored, done what armies might labor months to accomplish. The event is recorded in the historical literature of the period with a measured quality that is itself interesting to read. The writers of the time were accustomed to describing disasters, and they described this one in careful, factual terms. The location, the weather, the moment of the strike, the sequence of events from bolt to detonation to destruction, the final count of lives and buildings. There is very little in those accounts that dwells on horror. The horror was, presumably, self-evident. What the writers seemed most concerned to capture was the sequence, the causal chain from a single electrical event to everything that followed, because the sequence was what made sense of an outcome that might otherwise seem arbitrary or disproportionate. Brescia would eventually have lightning protection installed on its remaining buildings. The lesson was among the most expensive in the history of the technology. By the time the installations were made, there was no shortage of motivation. Between the careful triumph of Franklin's experiment and the catastrophic accident at Brescia lay a world in which lightning was newly understood as an electrical phenomenon, but not yet well understood as a controllable one. In the years immediately following Franklin's kite and key, natural philosophers across Europe and Russia were conducting their own experiments with atmospheric electricity, attempting to draw charge from the air, to measure it, to study its behavior under controlled conditions. These were not trivial investigations. They were, by the standards of the time, at the very frontier of what was known about the physical world. One such investigation was conducted in St. Petersburg, in the laboratory of a physicist named Georg Wilhelm Richmann, on a summer afternoon in August of 1753. Richmann had built an instrument for detecting atmospheric electricity, a grounded rod connected to an insulated lead that terminated in a small metal globe suspended above a dish of water, with a linen thread attached to measure the accumulation of charge. It was, in its way, a descendant of the same line of thinking that had produced Franklin's kite, a means of bringing the electrical activity of the atmosphere down into a room where it could be observed and recorded. On the afternoon of August 6th, Richmond heard the thunder of an approaching storm and returned to his laboratory to observe the apparatus. He had invited an engraver named Sokolov to join him. Sokolov was there to make a visual record of the equipment and its readings, to document what the apparatus looked like when it was in operation during a storm. Scientific illustration of this kind was a normal part of how experimental work was preserved and shared. Sokolov would have arrived with his pencil and his paper, prepared to draw an instrument and its measurements. He was there to document a routine piece of laboratory work. What the apparatus was not, on that afternoon, was grounded. Richmond's instrument was designed to accumulate charge rather than to conduct it safely away, and in the moments before a direct discharge from the storm above, that distinction became the one that mattered. A globe of pale blue light, described in the account that Sokolov later provided as appearing suddenly between the metal globe of the apparatus and Richmond's forehead, leapt across the gap. Richmond died immediately. The room was left with a smell of sulfur, a scorch mark on the floor where the discharge had grounded itself through the physicist's body, and a great deal of very sudden silence. Richmond had been standing in his own laboratory, a few feet from an instrument he had built and operated many times before, during a thunderstorm he had specifically chosen as the right conditions to observe. His death was, in the terms available to his contemporaries, a laboratory accident, a miscalculation about the conditions under which the apparatus was safe to operate, in the same general category as the many hazards that experimental work in any era carries with it. It was also, by the record, the first death of a scientist specifically engaged in research on atmospheric electricity. What makes the event sit quietly in the historical record, beside the more celebrated story of Franklin's kite, is not only the contrast and outcome. One man draws a spark safely from a distance, another is killed by a discharge at close range, but the presence of Sokolov. The engraver had come to draw an experiment. He stayed to witness something else entirely. His pencil was still in his hand when it happened, by all accounts, and the description he later provided of the pale blue globe and the sound in the room and the physicist falling was the document that preserved the event at all. The illustration he had been hired to make was never completed. The written account he gave instead was, in its own way, the record of the afternoon that survived. Richmond was remembered, in the years that followed, as a cautionary instance, a demonstration of the gap between understanding what lightning was and understanding how to be safely in its presence. Franklin had recognized, almost from the beginning, that the same electrical force he was demonstrating could be lethal under different circumstances. His approach to the kite had been designed to keep the conducting path well away from his body. Richmond's approach to his apparatus had not included the same care. The difference between the two outcomes was, in the end, a matter of the specific geometry of conductors and insulation, and of whether the experimenter had accounted for the exact conditions that would prevail on that particular afternoon. Natural philosophy in the mid-18th century was not yet the kind of organized, institutionally cautious enterprise that later laboratory science would become. Experiments were conducted with considerable personal latitude. The standard of care was largely self-imposed. Richmond's death prompted serious discussion in the scientific circles of the time about the correct design of atmospheric electricity instruments and the appropriate conditions for their operation. It did not stop the investigations. It made them more careful. The Apollo 12 mission left Earth on the morning of November 14th, 1969, in weather conditions that were, by the standards of the era, considered marginal but acceptable for a Saturn V launch. There were clouds, there was rain. There was, in the launch records, a note that the conditions were within the established tolerances for the mission, and the decision was made to proceed. The Saturn V climbed on schedule, carrying its crew of 3 through the cloud layer above the Kennedy Space Center, and 36 seconds after it did, the sky attempted to return it. The first strike hit the vehicle at 36 seconds. The second arrived 16 seconds later. Both were lightning. Both were strikes induced by the launch itself. The Saturn V, trailing a long column of electrically conductive exhaust gases as it ascended through the charged clouds, had created precisely the kind of tall conducting structure that encourages a discharge to complete its circuit. The rocket had in effect extended the local electric field upward through the cloud layer and triggered the strikes that followed. Inside the command module, the effect was immediate and extensive. Warning lights came on across the instrument panel. Not a few lights, not a selective alert, but most of the lights. Fuel cells went offline. The guidance platform tumbled. The crew reported seeing, through their windows, a sky that appeared to be lit up around them. Pete Conrad, in the commander's seat, recognized almost immediately that the vehicle was still flying, that the Saturn V's independent control systems had continued to function normally, even as the command module's electrical systems registered a cascade of faults. The rocket was still ascending. The trajectory was intact. The crew was intact. What had failed was most of the command module's electricity. In Houston, at the mission control consoles, the data streams from Apollo 12 were producing readings that a number of very experienced flight controllers had never seen before. Systems were offline in combinations that didn't match any known failure mode. The pattern of the failures was unfamiliar. Most of the people in the room were working the problem from what they knew, which was considerable, but which did not, in that specific moment, include a satisfying diagnosis. One flight controller, John Aaron, recognized something. Aaron was 24 years old and had been at NASA for 4 years. A year earlier, during a simulation exercise, he had seen a particular configuration of strange instrument readings, a pattern in the data that didn't match any clean fault scenario, and had traced it back to a specific piece of equipment called the signal conditioning equipment, an intermediary device that processed sensor data before transmitting it to mission control. The SCE had a secondary operating mode that could be engaged by a switch setting in the cockpit. Aaron had remembered this detail. He now recognized the pattern on his console as matching what he had seen in that simulation. He called it to the flight director, "Tell the crew to try SCE to auxiliary." The instruction was passed to the spacecraft. Astronaut Alan Bean, in the lunar module pilot seat, knew what the SCE switch was and found it. He moved it to auxiliary. The instrument readings began to stabilize. The fuel cells came back online. The guidance platform was reset. Within minutes, the command module was operating again. The mission was intact, and Apollo 12 was continuing its trajectory toward the moon. There is a particular quality to this episode that is worth sitting with. Slowly, the mission was saved not by a response to a known failure mode, but by the memory of an unusual data pattern that a single person had noticed during a simulation a year earlier and retained with enough precision to recognize it again under entirely different conditions. The simulation had not been designed to teach anyone about lightning strikes. It had not been designed to prepare the crew or the controllers for the specific event that occurred on November 14th. The pattern had simply lodged in one person's memory because it was odd, and when the same oddness appeared again, in a real mission, at a moment when most people in the room were working from different information, it was available. The lightning that struck Apollo 12 twice in 52 seconds was induced by the vehicle itself, by the decision to launch in conditions that allowed the Saturn V's exhaust plume to complete an electrical circuit between the storm clouds and the ground below. After the mission, NASA revised its launch weather criteria to explicitly exclude conditions where lightning was active within a certain distance of the launch corridor. The strikes did not cause the criteria to be invented from scratch. They caused existing knowledge to be applied more rigorously. The gap between the knowledge and the application of it was the space that Apollo 12 had passed through. Conrad, Bean, and Richard Gordon completed the mission. They landed on the moon in the ocean of storms, a naming that, given the opening minutes of their launch, had a certain quiet appropriateness. The science was done. The samples were collected. The crew came home. The lightning that had tried to stop them at 36 seconds was already many hundreds of thousands of miles behind them by then, a fact of launch day that had been absorbed into the mission's record and filed under lessons applied. Roy Sullivan worked as a park ranger in Shenandoah National Park in Virginia for nearly 35 years, and during those years the park struck him 7 times. The first occasion was in 1942, when a bolt hit the top of a hill where he was standing and reached him by traveling down a small tree. He lost the nail from his right big toe. This is how the record of Roy Sullivan's encounters with lightning begins, with a toenail, a hill, and a bolt that found him where he was standing. Sullivan was struck again in 1969, driving a truck on a mountain road in the park, when a bolt reached through an open window and burned off his eyebrows. In 1970, a strike left a burn on his left shoulder. In 1972, his hair caught fire. In 1973, he was standing near a ranger station when a bolt struck him and set his hair on fire again, the same hair that had grown back from the previous fire, and the shock threw him backward hard enough that he reached for the nearest object, which turned out to be a watering can. In 1976, his ankle was injured. In 1977, a strike came while he was fishing, burning his chest and stomach, and he drove himself to the nearest hospital afterward. 7 strikes over 35 years. The Guinness World Records eventually recognized the total as the most lightning strikes survived by any single person whose encounters are documented by reliable record. The question that the record quietly raises is how to think about it, and the honest answer is that the statistical framing is both correct and somewhat incomplete. Lightning strikes are not evenly distributed. A park ranger working outdoors at high elevation in a region with active thunderstorm seasons for 35 years encounters conditions that a person spending those same years indoors or in a city does not encounter. Sullivan spent more time in lightning-prone environments than most people will in several lifetimes. The elevated exposure explains some proportion of his record. It does not explain all of it, and the researchers and statisticians who have looked at the record over the years have generally concluded that the distribution of his strikes is unusual, even accounting for the elevated exposure. Sullivan's own explanation, offered in various accounts during his lifetime, was that he was simply unlucky. He appears to have regarded the matter with a kind of dry acceptance that served him reasonably well, since the alternative, arranging his entire working life around avoiding the conditions that his job required, was not an option he was interested in taking. He kept working in the park. He kept being struck. There is a detail in the accounts of Sullivan's encounters that appears in several sources and is worth noting for the particular quality it gives to the record. He reportedly attempted, in later years, to take shelter under trees when he saw a storm approaching, a practice that is generally considered among the least effective responses to lightning risk. It is not clear from the accounts whether this practice continued after any of the individual strikes. What is clear is that the record continued, and that Sullivan was alive to note each subsequent occurrence, and that the final strike in 1977 was not the last thing that happened to him. He was, by that point, well enough to drive himself to the hospital. The Guinness recognition came during his lifetime. He was aware of it. It is a peculiar kind of distinction to carry through a working life, the documentation that the natural world chose you, repeatedly, in a way that no one else appears to have experienced. The 4 moments gathered here, a man with a kite in a Philadelphia field, the church vaults of Brescia in August, a physicist in St. Petersburg with his engraver standing nearby, the flight controllers in Houston reading impossible data off a Saturn V in the rain, a park ranger in the Shenandoah Hills standing in a field for the 7th time, belong to different centuries and different continents, and the people involved in them would not, most of them, have recognized any connection between their circumstances and the circumstances of the others. But the thing they all encountered was the same thing, the electrical discharge that moves between a charged cloud and the earth below it, following the path of least resistance through the air, taking what it finds when it arrives. Franklin understood, after the kite, that lightning was not a mystery of a kind that required anything other than physics to explain. The electricity he had drawn from the storm cloud was the same electricity he generated in his laboratory. The difference was one of scale. The implications of that understanding took many years to fully work through. The lightning rod followed from it, and the lightning rod changed the relationship between buildings and storms in ways that Brescia had demonstrated, at devastating cost, were necessary. The experiments in St. Petersburg and across Europe followed from it, with all the hazards that experimental work at the edge of understanding carries with it. The revised launch weather criteria of the post-Apollo 12 era followed from it, in the specific form of institutional knowledge being updated by an event that exposed what the existing criteria had not accounted for. Roy Sullivan followed from nothing in particular, or from the compound probability of 35 years of outdoor work in a lightning-active landscape, depending on how one wants to count. What connects these moments is not a narrative of progress or of danger overcome. It is something quieter. Each of these people encountered the same natural force at a moment when the full understanding of that force, its conditions, its probabilities, its exact mechanics, was either unavailable to them, or available but incomplete, or complete but not yet applied with sufficient care. Franklin had the best possible understanding of lightning that existed in 1752 and still stood in a field in a rainstorm with a metal-tipped kite. Richmond had the same understanding and was less careful about where the conducting path ended. The Apollo 12 launch team had detailed weather criteria and judged the conditions acceptable. Sullivan had 3 decades of experience in lightning-active terrain and was struck 7 times anyway. Lightning, as an object of human attention, has a long history of being understood more fully than it is accommodated. The physics clarifies, the precautions improve, the record continues. In Houston, in the minutes after Aaron's call about the SCE switch, there would have been a particular quality of stillness in mission control as the instrument readings stabilized and it became clear that the mission was going to continue. The kind of stillness that follows from a crisis, narrowly resolved before the full accounting of what had just happened has been made, when the immediate task, keep the mission alive, has just barely succeeded and the room can exhale. The Saturn V was above the clouds by then. The command module was drawing power normally. The crew was intact. The path to the moon, briefly interrupted, was open again. Franklin's spark, Richmond's pale blue globe, the vaults beneath San Nazaro, the instrument panel full of warning lights. Each of them was, in one sense, the same event taking place in different surroundings. An electrical discharge arriving at a conductor when the conditions were right, taking the path available to it, completing its circuit. Sokolov the engraver never made the drawing he had come to St. Petersburg to make. The sketch of Richmond's apparatus, the careful illustration of the instrument readings during a thunderstorm, the document that would have been filed and shared with the scientific societies of the era, none of it was completed. What Sokolov produced instead was a written account of the afternoon, a description in words rather than lines, preserved in the literature of the period as the primary record of what happened in that room on August 6, 1753. He had raised his pencil to record a piece of routine experimental work. He stood in a quiet room next to an instrument that had operated normally many times before in the laboratory of a physicist he had come to assist. His pencil was still in his hand when the afternoon changed. The drawing he had come to make was never drawn. The record of what happened instead, in his own words, was kept. Rain is falling through a forest canopy somewhere in the tropics, not the heavy curtain of a storm still in progress, but the quieter, more patient rain that follows one. The drops move through layers of broad leaves, losing speed, collecting briefly on the underside of a frond before falling again, arriving at the soil below in a soft and continuous percussion. The ground absorbs them. What those drops carry is not only water. Dissolved in that rain, in concentrations too small to see or taste, are nitrogen compounds. They were made minutes or hours earlier, not by any living thing, but by lightning. A bolt somewhere upriver or over the ridge or above the canopy on the far side of the valley broke something open in the air that would otherwise have stayed closed for a very long time. Nitrogen makes up roughly 78% of the air. It is everywhere and almost entirely unavailable. The two nitrogen atoms in each molecule are held together by one of the strongest bonds in chemistry, a triple bond. Three pairs of electrons locked in a configuration that most biological processes cannot touch. Plants cannot use it. Animals cannot use it. The molecule simply floats, inert, through every breath and every wind, abundant and inaccessible at the same time. Lightning changes that. The extraordinary heat of a return stroke, the same narrow channel of superheated air that produces the visible flash and the sound that follows, is enough to break that triple bond. The nitrogen atoms, briefly freed, combine instead with oxygen, forming nitrogen oxides. These compounds are soluble. They dissolve into moisture in the air, into rain droplets and cloud water, and they fall. They soak into soil. They become, over the hours that follow, part of the chemistry available to roots. The contribution is not enormous in absolute terms. Estimates place lightning's share of total annual global nitrogen fixation somewhere between 5 and 8%. The majority of fixed nitrogen comes from microbial processes, bacteria living in soil and in the root nodules of legumes, working continuously and without drama. But the lightning share is abiotic, meaning it requires no living intermediary. It needs no microbe, no root, no enzyme. It needs only the bolt and the rain that carries what the bolt made. Some researchers studying the chemistry of early Earth have found this worth noting. Before life had established the microbial networks that now handle most nitrogen fixation, lightning may have been among the few available paths by which nitrogen entered the prebiotic soup, the warm, dilute, chemically active water from which, over immense spans of time, the first self-replicating molecules eventually emerged. The nitrogen in those drops falling softly through the present-day canopy is following a very old road. The drops land on the soil. They soak in. By morning, some fraction of what they carry will be available to the root systems extending through the first few centimeters of earth. Not because anything dramatic has happened, but because a bolt fell somewhere. The rain gathered what it made, and the forest floor received it. The process is quiet from start to finish. The loudest part happened miles away and hours ago. It is useful to sit with the scale of this for a moment. Lightning is not an occasional visitor to the planet's surface. On a global basis, roughly 40 to 50 lightning flashes occur every second. Not per hour, not per minute, per second. In the time it takes to breathe in and breathe out, somewhere between 80 and 100 bolts will have completed their path between cloud and ground, or within clouds above the surface. The total for a year runs somewhere between 1.5 billion and 2 billion flashes. This is not uniformly distributed. The land masses of the tropics account for the great majority of global lightning activity, and within the tropics, Two regions stand out with particular clarity. The mouth of the Catatumbo River in Venezuela, where the river opens into Lake Maracaibo, experiences lightning so frequently and so persistently on as many as 250 nights per year, for hours at a stretch, that for centuries it served as a navigational reference for sailors in the Caribbean. The Congo Basin in Central Africa produces lightning activity at a scale that has no equivalent in the Northern Hemisphere. Both regions sit in places where warm, moisture-laden air rises rapidly, where the geography and the wind patterns conspire to build storm systems with reliable consistency year after year. Together with thunderstorm activity over other tropical land masses, these two regions function as the primary generators of what physicists call the global atmospheric electrical circuit. This circuit is not a metaphor. It is a measurable, continuous electrical system in which the surface of the Earth holds a net negative charge. The ionosphere, the upper layer of the atmosphere, beginning roughly 60 kilometers above the ground, holds a net positive charge, and the potential difference between them is approximately 300,000 volts. Thunderstorms maintain this separation. They act as generators, pushing current upward through the atmosphere. Lightning is the return path, the current flowing back down. Without the continuous output of storms, the circuit would discharge and equalize within roughly 40 minutes. It has not equalized. It has been running more or less stably for as long as the planet has had an ionosphere and weather. The circuit does something else. It produces a resonance. When a lightning return stroke occurs, it releases electromagnetic energy across a very broad range of frequencies. Most of that energy disperses and fades quickly, but some of it, the portion at extremely low frequencies, enters the cavity between the Earth's surface and the ionosphere and begins to propagate around the planet. The Earth's circumference is approximately 40,000 kilometers. At the right frequency, a wave traveling at the speed of light will complete a round trip of the planet in the time it takes to sustain one full oscillation. That frequency is approximately 783 Hertz. This is the first Schumann resonance. The physicist Winfried Otto Schumann worked out the mathematics of this in 1952. He predicted that the cavity between the ground and the ionosphere, continuously excited by global lightning activity, should exhibit standing waves at specific resonant frequencies, 783 Hertz, and a series of harmonics above it. The prediction followed from basic principles of electromagnetic wave propagation in a bounded cavity, and it was not immediately tested because measuring electromagnetic waves at frequencies below 10 Hertz requires specialized equipment and considerable patience. Confirmation came within a few years, and what was confirmed matched what Schumann had calculated. The resonance is there right now. At this moment, the Schumann resonance at 783 Hertz is moving through the cavity between the surface of the Earth and the lower ionosphere. A wave whose length equals the circumference of the planet, present at every point on the Earth's surface at once, sustained not by any machine or transmitter, but by the ordinary background hum of global lightning. 40 to 50 bolts per second, each one releasing a brief electromagnetic pulse, collectively maintaining a planetary standing wave that has been ringing since before any human being was alive, to wonder what it was. The frequency 783 Hertz falls within the range of human brain activity during certain states of reduced alertness. This observation has attracted considerable attention and not a small amount of speculation. The scientific position is measured, the resonance exists. Human brain activity in certain states does occur near similar frequencies, and the causal relationship between the two if any exists, is not established. What is established is the resonance itself, real, measurable, global, and older than the species that eventually measured it. Lightning does not only fix nitrogen and maintain an electrical circuit, it also burns things. In the United States alone, lightning ignites an estimated 10,000 fires per year. On a global basis, lightning is the primary natural cause of wildfire. In the boreal forests of Canada and Alaska, and in the dry pine forests of the American West, lightning sparked fire is not simply a hazard, it is a process. The forests in these regions did not evolve despite fire. They evolved with it over millions of years, under conditions in which lightning regularly cleared undergrowth, released nutrients from standing dead wood, and opened the canopy in ways that allowed specific species to establish themselves. The fire was the condition, the species came after. The jack pine offers one of the clearest examples. Its cones are serotinous, a word that means late opening. Under ordinary conditions, sealed with resin, a jack pine cone will remain closed for years. The resin melts at approximately 50 degrees Celsius. Fire provides that temperature. After a fire passes through a stand of jack pines, the cones on fallen branches and on the ground open and release their seeds into ash-covered soil that has just been cleared of competing vegetation, enriched with the mineral residue of what burned, and opened to sunlight by the loss of the canopy above. The jack pine has arranged itself over evolutionary time so that the conditions it requires for reproduction are precisely the conditions that a fire creates. This means that a lightning strike in a dry boreal forest in late summer is not, from the perspective of the forest's long-term biology, a disaster. It is a reset. The nutrients locked in standing wood and in thick duff are released. The dense shade that suppresses young trees is briefly lifted. Species that require mineral soil and full sun to establish, species that cannot compete in an intact, closed canopy forest, find their moment. The fire moves through, and in the weeks and months that follow, the forest begins again from a different starting point. None of this requires a human observer to notice it or approve of it. It has been happening in these forests for longer than any human record. The pattern visible in a boreal forest recovering from a lightning fire is the product of millions of cycles of the same sequence: a dry summer, a bolt from a passing storm, a fire that burns until the rains come, and then the slow, green, patient return of the things that were always going to come back. Fire ecologists working in these forests have spent considerable effort disentangling lightning-caused fires from human-caused ones, and from the historical record of suppression, the period beginning in the early 20th century when most fires in North American forests were extinguished as quickly as possible, before it became clear that suppression was accumulating the very fuel loads that would eventually make fires larger and more difficult to manage. The lightning fires that would have cleared that fuel in smaller, more frequent cycles were stopped. The result, in many regions, was not a safer forest. It was a forest holding more combustible material than the one that lightning had historically maintained. This is not a simple story with a clean lesson attached to it. Forest fire ecology is complicated in ways that ecologists continue to work through, and the relationship between lightning fire, human fire, and managed suppression varies enormously by region and forest type. What is simple is the starting point. Lightning has been setting fire to the world's forests for as long as there have been lightning in forests, and many of those forests grew in a form shaped around that fact. Lightning leaves other traces that do not burn and do not dissolve. Sandy beaches and sandy desert surfaces sit mostly undisturbed until a bolt travels through them. When the current of a lightning strike passes through soil that is rich in silica, quartz sand being the most common form, it superheats the material along the exact path of the discharge. The temperature is sufficient to melt and fuse the sand grains together. In the milliseconds that follow, the fused material cools into glass. The result is a fulgurite, a glass tube, rough and pale, branching slightly where the discharge branched, following exactly the geometry of the channel through which the bolt traveled. Fulgurites are fragile. The glass is thin and full of irregularities, and a fulgurite pulled from the sand without care will break into segments at the first point where the discharge changed direction. When removed intact, they can extend 2 or 3 meters in length, occasionally deeper, depending on the moisture content and composition of the soil. In cross section, they are narrow, often only a centimeter or 2 in diameter, smooth on the interior surface where the glass formed directly against the current, and irregular on the outside where partially melted sand grains adhere in the process of cooling. A fulgurite holds something that almost no other natural object holds, the exact three-dimensional shape of a lightning channel in the moment of its passage through a solid medium. The bolt that made it lasted a fraction of a second. The glass it left behind can persist for thousands of years if the surrounding soil remains stable. Researchers have used fulgurites found in desert sediments as a geological archive, a record of where lightning fell and with what frequency, across time spans that long predate any human record of storm activity. The distribution of fulgurites in ancient dune fields can indicate whether a region was experiencing the kind of frequent, intense storm activity capable of producing ground strikes in periods too remote for any other kind of atmospheric record to reach. There is something worth pausing on in this. A lightning bolt, the fastest, hottest, most transient thing in the ordinary atmosphere, makes its most lasting mark not in the sky, but in the ground, not in light, but in glass. The flash is gone in 200 microseconds. The fulgurite remains, cooling slowly in the dark below the surface, preserving the shape of the channel in a form that outlasts the storm by millennia. The same bolt that produced the glass also produced a sound. The thunder from a single strike takes roughly 3 seconds to travel 1 kilometer through air at ordinary temperatures. By the time someone standing a mile from the strike heard the sound, the bolt itself had been gone for several seconds. The light reached the observer nearly instantaneously. The sound arrived later. The glass and the sand formed and cooled in the interval between. These three things, the flash, the glass, the sound, are all the same event, arriving in sequence in different forms on different timescales, one lasting a fraction of a millisecond, one cooling over minutes, one traveling through air at 340 meters per second, carrying the low frequencies that are felt before they are heard. Thunder is the sound of air expanding. The narrow channel of a return stroke heats to approximately 30,000 Kelvin in a few microseconds, a temperature the surrounding air cannot accommodate without moving. The channel expands outward supersonically. The initial expansion is a shock wave. A short distance from the channel, the shock wave subsides into an ordinary pressure wave, the rolling sound that follows a visible bolt. The rumble and duration of thunder reflect the length and geometry of the channel above. A bolt that extends for 2 kilometers horizontally produces a sound that arrives from different distances along its length at slightly different times, so the rumble can continue for several seconds after the first crack. On a night when lightning is occurring nearby, and especially on a night when storms are building rather than passing, the thunder from one bolt overlaps with the thunder from the next, and the sound becomes more or less continuous at some frequencies. The low end of thunder, The components below about 100 hertz can carry for distances of 100 kilometers or more, losing the crack and retaining only the low, steady roll. Sailors have historically used distant thunder as an indicator of storm systems they could not yet see. The sound traveled ahead of the storm. The electromagnetic component of a lightning strike travels rather further. A single large return stroke releases radio energy detectable at distances of thousands of kilometers in the very low frequency range. Systems designed to detect and locate lightning strikes by measuring the arrival time of their electromagnetic signatures at geographically separated stations can place a strike's location anywhere on Earth to within a few kilometers, essentially in real time. The global network of lightning detection stations currently in operation maintains a near continuous picture of where lightning is falling across the planet, updated every few seconds, fed by sensors that pick up the brief pulse of each bolt the way a microphone picks up a sound. This means that at any given moment, the location of the 40 to 50 bolts per second falling across the globe is known to within a few kilometers, logged and stored. The accumulated data from years of this monitoring has produced the lightning density maps that show the Catatumbo and the Congo as the brightest points, the most struck places on the planet, and that show the rest of the world arrayed in gradients from highly active to rarely struck, with the oceans generally quieter than the land masses, and the high latitudes quieter than the tropics. The maps also show something else, the year-to-year consistency of where lightning falls. The hot spots remain hot spots. The quieter regions remain quiet. The geography of lightning density is driven by topography, land-sea temperature contrasts, moisture availability, and the patterns of atmospheric circulation that do not change substantially from one decade to the next. A hilltop that attracted lightning in 1970 attracts lightning in 2020 for the same reasons: its elevation, its conductivity, its position in the local landscape. The map is not random scatter. It is the long, patient signature of the atmosphere doing what it does. This patience is worth sitting with because it is one of lightning's least obvious qualities. The bolt itself is fast, among the fastest processes in the ordinary atmosphere, developing over microseconds and completing in fractions of a second. But the conditions that produce the bolt are slow, accumulating over hours as charge builds in a developing cloud, and the geographic patterns that determine where bolts fall are slower still, set by landforms that took millions of years to assume their present shapes. The lightning is the fast event at the top of a very long, slow process. Early Earth had lightning. This is not a speculative claim. The conditions required for lightning, a planet with an atmosphere containing gases that can be ionized, sufficient convective activity to build charge separation, and a conducting surface to complete the circuit, were present on Earth well before the first life appeared. Some models of the early atmosphere place significant electrical activity in the period before the origin of life, when the atmosphere was rich in methane and ammonia, and the surface was largely ocean. The chemistry produced by lightning in that atmosphere, the nitrogen fixation, the production of organic molecules from simpler precursors, is one of the candidate processes by which the chemical complexity required for life might have assembled itself, slowly, over hundreds of millions of years played in warm water receiving the output of repeated electrical discharges from above. Stanley Miller and Harold Urey demonstrated in 1952 that passing electrical discharges through a mixture of gases thought to resemble the early Earth's atmosphere produced a variety of organic compounds, including amino acids. The experiment used a spark discharge to simulate lightning. The result was widely reported as a demonstration that the building blocks of life could arise from chemistry and electricity alone without any biological precursor. The full picture is more complicated. The composition of the early atmosphere remains a matter of active debate, and the gap between amino acids and a self replicating molecule is enormous, but the direction of the finding has not been overturned. Lightning like electrical discharge in a reducing atmosphere does produce organic chemistry. It did so in 1952 in a laboratory in Chicago. It has been doing so on this planet since before the planet had cells. The planet also had, from a relatively early point in its history, the Schumann resonance. As soon as there was an ionosphere and sufficient lightning activity to maintain the global circuit, the resonance was present. It has been ringing at approximately 783 Hz through every subsequent era of the planet's history, through the formation of the first continents, through the Cambrian explosion of complex animal life, through the rise and fall of every species since. It was ringing when the first forests grew and when the first lightning-sparked fires burned through them. It was ringing through the period when the jack pine was evolving the serotinous cone. It is ringing now in the cavity between the ground and the ionosphere, at a frequency too low to hear, passing through every location on the surface simultaneously. The fulgurites in the sand preserve a record of individual bolts. The Schumann resonance is the continuous background of all of them together, too low and too broad to isolate, a sum rather than a signal. The rains that follow tropical storms carry nitrogen compounds made by lightning into the soil below the canopy. The soil receives them. The roots take up what they can use. In the weeks and months after a lightning-sparked fire in a boreal forest, the ash-covered ground opens to sunlight and receives seeds from the split cones of jack pines. The shoots that emerge are small. They take years to become the trees that in another dry summer, another passing storm, another bolt, will burn again and begin the cycle from a different starting point. Nothing in this process is hurrying. The fire was the condition. The growth is the response. The next fire is already written into the resin on the cones of the trees that will eventually carry it. There is a quality to all of this that is difficult to name precisely. Lightning is fast, the fastest ordinary process in the atmosphere, but the systems it is part of are old beyond any intuitive grasp. The nitrogen cycle is as old as life. The global atmospheric electrical circuit has been running for hundreds of millions of years. The Schumann resonance has been ringing since the ionosphere formed. The serotinous adaptation of the jack pine took millions of years of fire cycles to establish itself. A fulgurite pulled from ancient desert sand might hold the shape of a bolt that fell before any human being existed to see it. The individual bolt is a fraction of a second. The context that produces it and the effects it sets in motion extend in both directions across timescales that dwarf the bolt entirely. What looks from the ground like a brief and violent event is, from a slightly wider perspective, one pulse in a system that has been cycling without interruption since long before there was anyone to watch it. The rain through the canopy continues. The drops arrive at the soil with less force than they had in the upper leaves, slowed by each surface they have glanced off on the way down. The nitrogen they carry soaks into the first few centimeters of earth and begins to move, slowly, into the chemistry of root and soil. Somewhere above the clouds that produce that rain, the Schumann resonance is present, 783 Hz, a wavelength of 40,000 kilometers, passing through the soil and through the rain and through the air above the canopy, without distinction or effort, maintained by the continuous output of every thunderstorm currently active anywhere on the planet.